Hi everyone, my name is Ridvan Aksu. Today I'm going to present our work 3D scene reconstruction from multi-sensor EO-SAR data with our collaborators Mahbubur Rahman and Dr. Sevgi Gürbüz from University of Alabama. We are all part of our laboratory of computational intelligence for radar. 3D scene reconstruction. So 3D scene reconstruction, it provides an in-depth knowledge about a remote scene. It gives us information about objects and their relative 3D positioning. It has lots of applications. In military, there are reconnaissance, real-time tracking; in civilian, disaster relief, civil design and planning, scientific measurement and modeling, agricultural planning. And there are lots of ways to do that. Synthetic aperture radar, electro-optical signals, and LiDAR are the main three ways of doing it. The images that in this slide show that the top image is a 2D SAR image of from Gacha volumetric SAR dataset. It shows a parking lot with lots of cars, and the bottom image is electro-optical image version of the same parking lot. SAR-based image is a popular imaging type. It is especially popular for remote scenes. It can achieve 2D imaging with high resolution, in especially submeter resolutions. It can be achieved in real time. It can also be used for 3D imaging using InSAR, TomoSAR, and other versions. But it is computationally intensive, it's challenging to do real time, and some types of it, like strip-map type SAR imaging, has occlusions via objects. And one disadvantage is you don't have any color information of the scene, so you may not be able to differentiate objects when they are not immediately recognizable. Multi-sensor imaging is used for combining multiple imaging techniques. It allows overcoming disadvantages of individual imaging techniques, and it can also be used to achieve a faster computation. So, combining SAR and EO, synthetic aperture radar, and electro-optical imaging can provide submeter imaging of an object as shape, location, angle via SAR, and high-resolution texture, color, and 2D location from EO, and exploiting correlation between these two during the imaging phase can allow robust and fast 3D imaging achieved by using electro-optical image to detect object boundaries and synthetic aperture radar to detect object height. Outline of this presentation is as follows. First, I will briefly discuss related work, and I will discuss multimodal imaging, which is what we are proposing in this work. It includes directional SAR imaging, then electro-optical based object modeling, and height-based imaging. Then we will apply our framework in Gacha experiment data. Then we'll conclude our presentation. So, this is the first work to investigate real-time electro-optical SAR fusion during imaging phase, as we know. So, there are lots of works regarding 3D SAR reconstruction, like, for example, tomographic SAR, or using electro-optical structure from motion for 3D imaging. Also, there are lots of works discuss electro-optical and SAR fusion in various accuracies and speeds, but we don't have a complete work that can be achieved in real time so far. Proposed multimodal imaging goes as follows. First, we use electro-optical image to model object shapes. Then, we use SAR imaging in various heights and direction to create directional images based on object angle in multiple height profiles. Then we combine each of these height profiles with the given object model from electro-optical image. Then we combine these multiple height profiles, create a 3D object. Directional SAR imaging uses angular SAR data from particular angles. So circular SAR uses a 360-degree pass around the scene to create a 2D or 3D SAR imaging. Objects return high power to radar, especially when they are perpendicular angle with no blocking. So we use object geometry to create the best return for each object. An example is a structure with falls facing north, east, south, and west will have the highest signal power when the radar is in the north, east, south, and west of the object. The image below shows a car SAR image for different angles from batch data. So the first image shows the radar return when we only look at the radar returns from when it is the east of the vehicle. When we have south of the vehicle, when we have west of the vehicle, and we have north of the vehicle. And the final image shows the final structure, which uses all four angles together. Important thing to notice here is in the 360-degree image, we don't have any return for the south of the car, which shows us that when we look at particular angles, signal return might be higher, which allows us to see the objects more clearly. EO-based object modeling uses an electro-optical signal corresponding to the same SAR signal. However, due to lack of data, we are not being able to use an actual electro-optical based object modeling here, so we are creating a EO image model for this work, which is precisely what we aim to do when we have the electro-optical image itself. So, using an electro-optical image, you can detect object boundaries. So, let's assume that the right shape is from different height profiles, sections of a building, and the figure on the bottom shows the same as seen from its 2D shape EO image. So we use these boundaries to assign surface to each object based on its facing direction, and we create submodels for each cardinal direction. This can be applied also to additional directions based on total weight on that direction for that particular SAR image. It doesn't have to be just 4 angles, but can be extended as much as needed. Height-based imaging allows us to create SAR images in different heights given our EO model. So for each height, we compare the return power of selected direction and other directions from our directional SAR images to based on our EO model to see the actual presence of the object on that particular region. So pseudocode of our work is as follows. First, we create a model using an EO image. For each object, we detect surfaces and generate that model. Then we create SAR for each height and for each side. So we create a SAR image, then we normalize and ratio signals. Important thing here is, although we are creating multiple SAR images for each side, since we are going to look from different angles, a narrow set of angles, this is not as intensive as creating a whole 360-degree image. Then we create 3D image by combining each height and each side. But first we look at it is return power, SAR return power on the correct side of the model corresponding to the SAR image, then compare with the other angles, either opposite angle or a combination of all 3 angles. Then we discard negative values. We used Gacha multipass data to test our framework. We use Gacha volumetric SAR dataset version 1.0 from AFRL, which only has public access for parking lot data. So due to lack of electro-optical image for that corresponding dataset with the same usage of the parking lot, so we don't have cars same positions as an electro-optical image, we created a modeling based on that car dataset provided with Gacha SAR dataset. And here it is precisely what we are going to do if we had that electro-optical image and we would create that SAR electro-optical image model from that dataset. But our method can be generalized for a more general dataset with fixed structure. First, we created a parking lot model given car parameters. We divide each object into 4 surfaces, namely east, south, west, north. Then we use this models as the object surface to use on SAR images. We repeated this for each direction and repeat for each SAR height. And the final image shows the combination of 4 surfaces that amounts to a complete image of a car. The 6 figures show for 6 different height profiles our height-based imaging. So here we combined 4 different directions with SAR images and with given electro-optical image model. So here at z is equal to 0 meters, we show the mostly the surrounding boundary of the car. And when it goes to z is equal to 1, we see that that surface area becomes more cylinder, which reflects the car shape at z is equal to 1 meter. Then at z is equal to 2, we are now showing what only amounts to the hood of a car. Then at z is equal to 3 and 4, we get only noise or imperfect reflections from SAR, and z is equal to 5, we now started getting more returns, which corresponds to the interference from other cars or objects that's surrounding. So here we are cutting our limit at z is equal to 3 given our model. One thing to notice here is in our electro-optical model we have total 1, 2, 3, 4 sets of cars. A second set in the model shows 3 cars and the fourth set shows 2 cars. However, in Gacha SAR data, contrary to its car data set, there's only 2 cars in the second row and 1 car on the fourth row. So our method actually does not pick up any signal from SAR image corresponds to these 2 cars that are not present in the provided SAR images. So we can actually validate our findings from here by showing that we are only picking up the signal when it is present there. We want to work on optimization and improvement of this current work in future by using an EO-SAR pair for practical testing, optimizing the angular interval for best representation of edges in directional SAR, which currently we are using 90 degrees for each direction, but a narrower angle might provide a better representation of that surface and that edge. This needs to be tested. Time efficiency comparison with other 3D imaging methods, which shows that how we can achieve real-time imaging with our method. And noise reduction via autofocus that can eliminate noise in the height profile that doesn't present any actual image data, and also exploiting multipass data for more accurate and finer height profiling can be used. This allows us to create a more precise imaging by using similar methods that can be used in SAR, interferometric SAR, or other methods. Thank you for listening.